hopefully by now, everybody knows that we have an exam tomorrow. So the exam will be available on my courses from 3 p.m. to 7 p.m. Eastern Standard Time. I know that one student has approached me with a conflict. So if you have a conflict, please let me know and we can try to work something out. I will run a meeting here in Zoom from 5:15 to 7 p.m. in case you have questions. Um, Particularly, you may have seen, maybe when doing quizzes or when doing homework, maybe as you're reading something, maybe it doesn't make sense. So I'm sure you've had that experience in tests in the past as well. So we can handle those in that meeting time. So I think that this 4 hour block um, is certainly enough time to do the exam. I'm not trying to make the exam any harder than it normally would be. So hopefully we feel like, um, by the time we're done, that you feel like you have had the opportunity to demonstrate your understanding of the material. Does anyone have questions about the test before we get started with today's lecture? All right, we'll get started. So we've been talking about conservation of mass, right? And now this is kind of a chemical example, but I sort of like the pictures, right? So, the idea of conservation of mass is that if you have a control volume and you want to know how the mass changes in the control volume, you kind of have to count up everything that came into the control volume and everything that left the control volume, because we don't have the ability to just make mass appear or disappear with magic, right? So we're going to talk about how we try to account for this when we're doing thermodynamic problems, right? And this is important, especially moving forward, right? So we've done some work with closed systems, right? So just maybe a very brief review of how to do closed system problems, right? We start with our conservation of energy equation, right? The first law of thermodynamics. So if you are on the test tomorrow, if you're at a point where you feel like you don't really know what to do, start to think about the first law, right? And this is the general process. We have this first law for closed systems. We make some assumptions about the changes in the different kinds of energy. We have an equation for work. We can find typically the change in the internal energy. But to do that, we have to maybe fix states of water. So we need to know something about the phase if what's in our system is water. Or maybe we have to use the ideal gas law and some constant or variable specific heat analysis if what's in our control volume is air or some other ideal gas. So moving forward, the next part of the class is, well, what happens when we allow mass to come in and out of our system, right? And that makes the problem harder because, as we've seen, every little bit of mass has some energy with it. So in conservation of energy, when we start allowing mass to come in and out, we're going to have some extra terms here that talk about the energy coming in and out with the mass. But before we can account for the energy, we have to be able to account for the mass. So we need to know when mass is coming in and when mass is coming out. And the first step in that process is to say, like, what's the part of the universe that we're interested in, right? And we know this from closed systems where we had to define where our system was. Right now, in closed systems, there was no mass that could travel across this border that defined what our system was. But in open systems, mass can flow into and out of our control volume. So what we're going to need to be able to do is first define where the control volume is, right? So in a pipe, I think I said this before, where it's nice to have at least some of the walls of your control volume sort of butting up against something physical, like the inside wall of the pipe. But then you're going to have some parts of your control volume here where it's permeable to mass, right? So here, this part is sort of perpendicular to that wall so that the flow can go right through. So there's an inlet and an outlet. And before we ask ourselves what happens to the energy, we need to know what happens to the mass. So that's what we're trying to figure out now. We talked about looking at conservation of mass in an elapsed time way. This is maybe a little more I don't know if straightforward is the right word, but maybe the way that we humans are more used to thinking about this kind of problem. The mass I have at the end minus the mass I had at the beginning is equal to the sum of all the mass that we put in minus the sum of all the mass that we put out. Right? And we talked about this very special case called steady state. And at steady state, over time, the mass that's in your system doesn't change, because in steady state, no properties are changing, right? So if nothing changes with time, then the amount of mass in your system can't change with time either. And under this special case, this steady state condition, all the mass that comes into my system is equal to all the mass that goes out of my system. We also talked about maybe a way that's a little less intuitive to think about these problems. So now, instead of looking at how mass is accumulating or leaving our system, we're going to look at it at a particular instant, right? And this is now the rate at which we are storing or losing mass is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out. And this is the sort of version of this equation we're going to use most often in this class. When we use closed systems, we're often interested in how something in the system is changing over time. When we use open systems, our subscripts are going to depict not moments in time, but locations in space. So here there's one inlet and there's two outlets. So what are the mass flow rates at the inlets and the outlets? And what are the states of the whatever material is flowing through my system at the inlets and the outlets, right? Because you could, you can imagine something like an air conditioner where it takes air, hot air in from outside and blows cold air into your house. So there is this, if it's a window air conditioner, right? There's this change in the properties of the air as it moves through that system. So we'll be able to talk about how the energy has changed as we move through that system. Again, we can have this special condition where we're at steady state. And in steady state, if nothing is changing with time, that includes the rate at which mass is changing with time. So at steady state, the rate at which we're accumulating mass is 0, or dt by dm is equal to 0, which means that the sum of all the mass flow rates in is equal to the sum of all the mass flow rates out. We talked about this as kind of that special state where, I put a cup outside and there's a hole in the bottom, but it's raining just enough so that the mass flow rate that's coming in the top of the cup is equal to whatever mass flow rate is leaving through the hole in the bottom of my cup. So the level of the water stays the same. And because that level of water stays the same, I'm not storing any mass over time, and I'm not losing any mass over time. Right? So when we're at steady state, the sum of all the mass flow rates in is equal to the sum of all the mass flow rates out. And in this class, we're typically going to be interested in how different open system cycles operate when they're at steady state. So this steady state condition is going to become pretty important for us. So I'm going to go through a couple of examples, first looking at at elapsed time and then looking at a rate equation. Now the elapsed time one's maybe a little bit silly, but with 3 young kids at home, I spend a lot of my time watching Disney, especially now that they have their own streaming service, which, I often talk about, and maybe I'll do it for this class too, or maybe put some YouTube videos up, but I do talk a little bit about personal finance sometimes in classes that I've taught, and Disney is kind of the enemy of personal finance. So we were supposed to go there this summer because I was at a conference, and everybody who goes there says it's just Disney makes it real easy to spend money. So this is kind of the story that I like to tell here. I don't know if you've ever seen this one, but back when I was a kid, there was this cartoon called Mickey and the Beanstalk, right? Which is basically Jack and the Beanstalk with Mickey, being Jack, right? So they had this one cow, right? They live in this place that's pretty desolate, right? All they have is a cow, right? Mickey takes it to market. He meets some kind of, snake oil salesman who tells him, oh, yeah, I'll trade you your cow for these 3 magic beans, right? And Mickey's like, awesome, 3 magic beans. This is amazing, right? And he brings it home. And I think Donald kind of gets really upset at him, right? So he's like, oh, I don't know what's going on, right? And I think Donald takes the beans and he chucks them out the window, right? So now Mickey's feeling pretty bad, right? He feels like maybe he made a mistake, but he's going to try to make the best of it, right? So he's got these beans and he wants to water them because he traded a cow for him. He figures the least that can happen here is we at least get some beans to eat, right? So they got this reservoir, right? This reservoir has a lot of water in it. It's got 10 liters of water. And they're using this reservoir to water the beans, right? So on Monday, Mickey waters the beans 2.5 liters. He's feeling pretty psyched. He really wants to show that, these aren't just waste beans, right? Goofy on Tuesday, Goofy's on board, right? Goofy's a nice guy, 2.5 liters. He's like, I'm on Mickey's team here. Let's make the best of it. Donald is a little bit less excited. So on Wednesday, he only waters the beans 0.5 liter. Right? Mickey now adds 3 liters to the reservoir on Thursday, and he waters the beans 2 liters, right? So he takes some more water out of the reservoir. Goofy waters the beans 1.5 liters on Friday. He's maybe a little bit less excited now, right? So now the question is, how much water is left on Saturday morning? Right? So now this is an elapsed time. It's really a conservation of mass problem, right? But when we look at this, maybe we think, oh, how can this be conservation of mass? Because liters, as you may or may not know, are a unit of volume, right? Again, this might be confusing if you're used to imperial units, right? Because, if you're doing any cooking, right? So maybe in quarantine, maybe you're cooking a little bit, right? And people use ounces as both a measure of volume and a measure of weight, right? But here, liters and kilograms are 2 different things, right? So to get the mass, we'd have to multiply by the density, right? Or divide by the specific volume, because this is thermodynamics class. But if we make the assumption that the density or the specific volume are constant, then what's going to happen is our conservation of mass equation is going to look like conservation of volume. But we have to remember, conservation of volume is not a thing by itself, right? It's really mass that's conserved. And we'll see that better, we'll see that better in the next problem. Right, so we're going to assume that the density of water here is constant at 1,000 kilograms per meter cubed, or that the specific volume of the water is 1/1,000 meters cubed per kilogram. We're going to assume that we can neglect evaporation in the reservoir. So, these Disney characters are reasonably smart. They put a lid on the reservoir so that they're not, just constantly evaporating the water that they've saved inside their reservoir. Right, so elapsed time version of conservation of mass looks like this, right? So if we want to find out how much mass is left at the end, minus how much mass we had at the beginning, we add up all the mass that we brought in, and we subtract all the mass that we brought out. I didn't actually do the math here. If anybody did the addition and subtraction, maybe you can give an answer. But hopefully everybody can see, right? And intuitively, you probably knew this, right? Because you're human and you've probably done things like this before, right? So we had 10 liters, right? We took away 2.5. So now we're at 7.5. Now we're at 5. Now we're at 4.5, right? But Mickey adds 3, right? So we're at 7.5. Subtracts 2. We're at 5.5. And now Goofy subtracts another 1.5, right? So that means we're at 4 liters, I think, if I did that right. So 4 liters, we could then convert that to mass if we wanted to. So this is kind of how we do elapsed time. This is a bit trivial. Sometimes when you're doing problems like this, you might have to integrate over time to see how much mass is left. So if you were doing something like, let's say you had a big reservoir and a hole in the bottom, right? So it's the pressure or the weight of all the water that's the height of the reservoir, right? That's driving that flow out. So actually what happens is as the reservoir loses water, it's sort of, the driving pressure is reduced. So you actually, the velocity goes out, so the mass flow rate would change over time. So you might have to do some kind of integration. We don't do these kind of problems too often, so I don't want to spend a ton of time on this, right? But I thought I'd try to make this fun story. So I don't know if you've ever read the old version or seen the old version of Mickey and the Beanstalk. You know, the beanstalk grows really high. They go up, find out that the giant stole this magic harp or something, and there's a goose, I think, and golden eggs. So they steal all that stuff back, right? Because this is the old version, right? Where you just, you know, if somebody has something that you want, you just steal it, right? So now Disney maybe decided that that's not the best way to go. So I think in the new version of this story, you know, the giant comes down and they all become friends, right? So that's kind of how we deal with conservation of mass over time, right? Or this elapsed time version. Does anybody have questions about this type of a problem? So the rate version of these problems is maybe a little bit less intuitive, right? Now, this is a problem that's at least very much like your homework. And I don't know, I was going over the homework problem with someone in office hours today, and it might actually be the same problem, but I'm not sure if the properties are the same. But here we have a turbine. Now, if you don't know what a turbine is, don't worry. One of my friends, when I was taking this class, you know, he said what he learned was that a turbine, you know, looks like a triangle, or maybe a triangle with the tip lopped off, you know, that's expanding as we move left to right, right? And he said a compressor is the opposite way, where it's, you know, decreasing as we go from left to right. Now, hopefully, you know, he was saying that that was the only thing he learned from thermodynamics, and I hope that I hope you don't feel that way after this summer is done, right? But what a turbine does, right, is it takes high pressure, high temperature steam, so steam that has a lot of energy, right? We're learning a lot about this internal energy. So here what we're doing is we're taking steam that has tons and tons of energy, right? And now we let it expand, right? Because it's at a really high pressure. If you think about like a balloon, or if anybody has so if you think about a balloon, right, that's air under pressure, and if you pop it, the air in the balloon wants to escape, right? Or maybe, I don't know, I know everybody might not have access to these, but if you have or have seen a pressure cooker or an electric pressure cooker, you know, at the end, what happens is you have this vessel and it's sealed, and you have some water in it, and usually some other stuff because you're cooking, right? And then what happens is you boil that water. And because you boil that water, you generate steam, right? And we know the density of water is much higher than the density of steam, but I think by like 1,000 times usually, right? So now what happens is you know, the steam wants to take up more room than what's allowed, right? So the pressure just keeps getting more and more and more, right? Because you're pressurizing this container. And then what can happen is when you're done with your pressure cooker, if you don't let it sort of release naturally, you know, at least the one we have, you flick this valve and the steam shoots out, right? Because it wants to expand, right? It wants to go through. So what a turbine does is there's this steam that wants to rush out into this expansion. And what we do, you can't see the cross section of the turbine here, but there's basically fan blades here. So now what happens is that steam that's rushing through with all this energy moves over the fan blades, and that causes this shaft to rotate, right? So there we have this energy that we stored inside of our system by doing things like boiling the water, by adding heat, and also by, so first we took some liquid water, we compressed it up to a high pressure, and then we added a lot of heat. Usually we do this by boiling things or by burning things, right? So if you think about like a coal power plant, it boils water by burning coal. Or a nuclear power plant, it boils water by this nuclear reaction, right, which is exothermic. So we take the waste heat from that reaction, we use it to boil water, and that creates this steam. And this steam wants to expand, right? So it expands over these fan blades, and that causes this shaft to spin. Now, you can directly use that spinning shaft to maybe drive something like a compressor, right? Or you can connect it to something that maybe looks like an electrical generator, and that spinning shaft, then we turn that into electrical power, which we can put out onto the grid. So we won't talk about the energy. That's kind of a little bit what a turbine is. But in this case, we only want to know about the mass, right? So here we have some mass flow rate that's coming in, some mass flow rate that's going out at state 2. So what it tells us is that 20% of the mass leaves the turbine at this output port 2, right? It also tells us that the pressure and the temperature at state 2 are known, and we know the diameter at state 2 is 1/4 meter. At state 3, similar information. Here we don't know what percentage of the mass flow rate that comes in is coming out at state 3, but we're told the temperature and we're told the quality, so we could probably fix this state. We're also told that the diameter here is pretty big, 1.5 meters, right? At the inlet, I don't think we talked about this, but this is a high pressure, high temperature fluid. We're also told that it has A times V. Now it's tricky. This is one of those things in thermodynamics. We got all these letters in the normal alphabet, all these Greek letters, but oftentimes we use letters that kind of overlap, right? So in this case, this AV is area times velocity. So if you think about area times velocity, you would get some sort of length cubed, right? So like meters cubed over some unit in time. So this is a volumetric flow rate, right? Now it's important to remember what we said last time. There's no such thing as conservation of volume. So volumetric flow rate by itself doesn't necessarily help you unless you know the density is not changing, right? Or that the specific volume is constant. So this is what we know about the problem. We're asked to find the velocity at state 2 and state 3. So the velocity at these two different exit ports. So we're also told that this problem is at steady state. So now I look at this problem, right? And I got to think, so I know this is a conservation of mass problem, right? But I have to think, well, what version of conservation of mass are we talking about here? So first, it's maybe a bit of a hint that we have mass flow rates here, but maybe not necessarily, because you can have an elapsed time where you then say, oh, we have a mass flow rate and some unit of time, like an hour, how much mass left the system, right? So we do have a mass flow rate, which maybe makes me think the rate equation. I also have different ports here that are at different sort of positions in space, right? But I'm not exactly sure, right? So here, what I can think about, because they don't tell me some sort of time step, they don't tell me how much time went by. So now I'm going to think, okay, I'm going to use an instantaneous version of this equation, and I'm going to use it to try to find these velocities, right? And to do that, the problem has told me that the whole system is at steady state, right? So that means we turned it on a little while ago, and it's already kind of warmed up, right? So here, I'm going to use the rate equation because I don't know anything about some delta time, right? And I know that it's at steady state. So usually, this equation would be dm by dt is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out. But because this is at steady state, I know that dm by dt term is equal to 0. So if it's at steady state, nothing is changing with time, which means the amount of mass in my system is not changing with time. So I'm not storing or depleting any mass that's in the turbine, right? So even though it's a different, there are different elements of fluid, different mass that's in the turbine at any instant, it's still the same amount if you add it all up. So I know that the sum of the mass in is equal to the sum of the mass flow rates in are equal to the sum of the mass flow rates out. I also know from last class that we can define the mass flow rates as the area times the velocity, that's the volumetric flow rate, divided by the specific volume. Or if you'd like to think about this in terms of density, this would be density times area times the average velocity. So now I got an equation, and that's good. That's something, right? So what I like to do when I have an equation is check to see what I know and what I don't know. So here, I don't know the velocity at the inlet port. I don't know the area at the inlet port, but that doesn't matter because the problem told me that the area times the velocity, or the volumetric flow rate, was something, right? So I know that value. I don't know area at port 2. I don't know area at port 3. I don't know the specific volume at state 1 or state 2 or state 3. And I don't know the velocities because that's what the problem is asking me to find, right? So the first thing that I can do is I can say, well, sure, they didn't give me the areas, but they did give me the diameters. So the area at these different ports is going to be pi times r squared, or because they gave me a diameter, I can say pi d squared over 4, right? Usually I like to use pi r squared, but it doesn't really matter. You just have to remember to either divide by 2 before you square it or divide by 4 after, right? And then I can look at different tables to try to fix state 1 and state 2. For state 1 and state 2, they told me the temperature and the pressure. So I'm kind of really hoping that these end up being superheated vapors. Part of this is just because I know something about turbines. So turbines, we have steam that comes in. Your turbine probably is not going to be great if it's liquid water going in, unless you're talking about something like Niagara Falls, where there's kind of, this flow of water that's already moving, right? But typically when we talk about a turbine like this, it's steam that's entering, right, or superheated vapor. At state 2, they told me the temperature and the pressure. So I'm hoping that those are still independent properties, which would be true if it was superheated vapor. State 3, they told me that the fluid had a quality. So anytime that there's quality and you're talking about fluid, it means there's some kind of mixture of saturated liquid and saturated vapor. So I know here I'm going to look under the vapor dome. So if I can find those things, then I know the volumetric flow rate at 1. If I can find these specific volumes and these two areas, that's not too bad. It's still not something I can solve. I'd have one equation and 2 unknowns, but that's a lot better than one equation and like 7 unknowns, which is where I'm at right now. So I'm going to try to start working my way through this. But I still got this problem here, right? So I got this problem of I won't know what V2 and V3 are, right? But let's not worry about that yet, right? Because even after I do this, I'll have one equation and 2 unknowns, right? So now I know A1, V1. So this is the same slide that we just saw. I don't know why it's repeating, right? So I don't know these things, but there's a way for me to find them, right? So now I'm going to draw a state table, right? So my state table is going to look like this. It tells me the information that I know, right? So here I'm told the temperature and the pressure at state 1. I'm told the temperature and the pressure at state 2. And I'm told the temperature and the quality at state 3. I'm also told this isn't like a fluid property, but hey, if I'm going to make a table with all this information, I might as well write down the stuff that I know, right? So I know the diameter in meters at port 2 and the diameter in meters at port 3. I'm also told that the mass flow rate at state 2 is 20% of the mass flow rate of state 1. So I'm not going to go through fixing the states, but from here, I know that this is superheated vapor, right? You're going to know, hopefully you feel confident, hopefully looking up states, right? So here we can find the specific volumes of these 3 cases, right? So here we get some numbers, right? We put them on our state table. The areas we can find using the equations that we had before, and then we have area at state 2 and area at state 3. Here you can see that the area at state 3 is much, much bigger, right? Maybe that's because they're expecting more of the mass to come out there so that they want, they don't want to make a jet that's going to, have too high of a pressure, right? So, or too much of a velocity, right? So here we know that the sum of the mass in is equal to sum of the mass flow rates in is equal to the sum of the mass flow rates out. But now because I went through and I fixed all these states and I calculated my areas, I went from this case where I had 7 unknowns in this equation to this case where I have 2 unknowns in this equation, right? So it's progress. Unfortunately, it's not quite enough progress for us to be able to solve this problem, right? So we need some other equation. And I don't know what equation to use necessarily. I mean, I do because I've done this problem before, But maybe the first time I did this problem, I was like, man, I don't know what to do because I've already used conservation of mass, right? But the cool thing is here, I can use conservation of mass again, right? So I guess the other equation that I have is that they told me that the mass flow rate at 2 is equal to 20% or 0.2 the mass flow rate of 1, right? So now if we're at steady state, I know that the sum of all the mass flow rates in is equal to the sum of all the mass flow rates out, right? So if everything that goes in has to come out at the same rate, and I have 100% of the mass flow rate going in and 20% of the mass flow rate going out at state 2, that must mean that I have 80% of that mass flow rate going out at state 3, right? Or mathematically, I know that m dot 1 is equal to 0.2 m dot 1 plus m dot 3. I can isolate for m dot 3, and I find that m dot 3 is 0.8 m dot 1. This is great, right? Because now I know this, right? So now I can go through and I can find m dot 1, right? So here I know this volumetric flow rate because they told me, right? Meters cubed per minute. It's always, I prefer units. Well, first, I prefer metric units, but I always prefer the units to be in kind of their basic form, right? So the basic unit of time is seconds. So here, if I didn't write it out right in my known information, if I didn't convert this to meters cubed per second, then I would really be itching to do it now because I track my units in my calculations and I see, I really don't like that idea of minutes, right? So here, this part's cool, right? This specific volume is in meters cubed per kilogram. I like that, right? So here, if I work this out, right, the meters cubed are going to cancel, the kilogram is going to come up on top, and I get 666.5 kilograms per minute. I don't like kilograms per minute. Like I said, I would prefer it to be kilograms per second, right? So to get rid of the minutes on the bottom, I know that there's 1 minute for every 60 seconds. Now my minutes are going to cancel, and I'm going to get 11.1 kilograms per second. So that's the total mass flow rate in, right? Now I know that 20% of that is going to come out at state 2, right? Okay, so 20% of that, right? I can do this on my calculator, right? And maybe even in my head, right? So 0.2 times 11.1 is just about 2.2, right? Now, if 20% of the mass is coming out here and all of the mass has to come out, then 80% of the mass comes out at state 3, and we're going to get 89 or 8.9 kilograms per second. So this is good because now I know the mass flow rates at all 3 of these different places. Okay, well that's good. But the problem doesn't ask me for the mass flow rates. The problem asks me for the velocities. So now I have to go back and remember that our mass flow rate, one of the ways we can define the mass flow rate is the area times the average velocity divided by the specific volume. Now, I'm never actually going to end up using the first version of the conservation of mass equation that I had, but I'll use each of the pieces, right? So here, I know that m dot 2 is equal to AV2 over specific volume 2, right? I can isolate for the velocity at state 2. I put the numbers that I know in, right? And here, so this is good. The kilograms are going to cancel. I'm going to get 1 over seconds over here. This is going to be meters cubed divided by meters squared. So I get something in meters per second, which is great because this is the velocity. So it should be some unit of length divided by some unit of time, right? So that's good for state 2. Now, I can't just say, remember with the mass flow rates, I said, oh, once I know, m dot 2, it's going to be 20% of the total, right? So like I can multiply that mass flow rate by 4 and get 80% of the total. I can't do that with the velocity, right? Because we have conservation of mass. We don't have conservation of volume, and we don't have conservation of velocity. We have conservation of mass. So we have to go back to m dot 3, right? Remember, this is a different area than A2. So presumably the velocity is going to be different because the specific volume is different too, right? So now, again, we do the same sort of mathematics here, the same arithmetic, but we put different numbers into our calculator because we have a different mass flow rate, a different specific volume, and a different area, right? But we still get, the same units. We get a velocity of 10.7 meters per second. And you might look at this and say, wow, it doesn't make a lot of sense, right? Because there's 4 times as much mass coming out at port 3, right? But its specific volume is different and its area is different. So I don't know. Intuitively, I don't know if it should be bigger or smaller. But I know that my units are right, so I can't prove that my answer is wrong, right? And as I always say, right, it's, if I have to choose between being able to prove myself wrong and not being able to prove myself wrong, I know what answer I'm going to pick, right? So now I can put all this information in here, and I see that my velocity terms are known. In this problem, I'm never going to know the velocity at the inlet because I don't know the cross-sectional area at the inlet. But that's okay, because the problem only asked me for the velocity at the 2 outlets. So now I'm done, but I got to ask myself, does it make sense? So I feel confident because my units are right? I get the velocity in meters per second. So that's good, right? The relative magnitude, I don't know if it makes sense, right? V2 is bigger than V3, which is maybe not what I assumed. Although, I got to remember, at state 3, there's some liquid water, right? And because the density of the liquid water is higher, then, it moves more slowly because the molecules are more densely packed, right? So the mass flow through 2 is 4 times smaller than through 3. So you might expect that V3 would be bigger than V2. But the fluid is 5.5 times less dense through 3, again, because of the water. So you might expect something different if you just look at the fact, so again, you might expect that the V2 would be less than V3, right? But the area is a real big difference here, right? Because the area at 3 is 36 times bigger than the area at 2, right? And you might not see this at first because remember, area scales with the radius squared, right? So if you just make a small change in the radius, you get kind of an outsized change in the area, right? So I don't know if this velocity really makes any sense or not, right? But I do know that mass is conserved, so I used that equation to get to this answer, and I know that my units are right. So it makes sense that we have to account for, the change in density, the change in area, the change in, well, specific volume is density, right? Because there's no such thing as conservation of volume, and there's no such thing as conservation of velocity. Here in the universe that we live in, we see that there's such a thing called conservation of mass. So we have to be careful that we're using that to account for the stuff that's moving through our system and not just looking at the volumes or the volumetric flow rates or the velocities. So I think that's all for today. Does anybody have any questions either about the stuff that we talked about today or about the test tomorrow? All right, if not, I'm happy to let you go. Thanks for coming by. And as I said, we will post the exam at 3 o'clock. Well, I say we, but it's really just me over here, right? We'll post the exam at 3 p.m. Eastern tomorrow. So good luck. If you have any questions before that, shoot me an email, particularly if you have a conflict. So like I said, I did have one student who notified me that they have a conflict with work. So that's something that we can work around. And if you do have some other kind of conflict, I can try to work with you on a time. Thanks very much, everyone. I will.